Welcome to the deep dive. Today, we're really getting into a core concept for anyone in materials science: phase equilibrium in a one-component system.
Mhm.
You've given us a pretty dense chapter on the thermodynamics here, and, our mission is to cut through all the derivations and really give you the essential physical understanding of how a material chooses its state.
That's right. We're essentially looking at the blueprints for materials, the phase diagrams. These tell us exactly how a material is constituted under different temperatures and pressures. And to build those blueprints, we have to rely on, well, fundamental thermodynamic principles.
So before we dive headfirst into the math, let's just establish the key players. We're talking about phases. For anyone maybe new to this, how do we define a phase so it's not just, a pex of the material?
A phase is a physically distinct, homogeneous region within a system. So think of ice floating in water. The ice is one phase, the liquid water is another.
Got it.
They're separated by a clear interface, and you can, in principle, mechanically separate them. They're defined by their state solid, liquid, gas, their crystal structure, and their specific degree of internal order.
And the fundamental rule that governs when they all exist together, when they stop changing, what defines that?
It's all about the Gibbs free energy. G stability at constant temperature and pressure is always governed by G. The system will naturally move toward the state that minimizes its total Gibbs free energy.
And if it gets to that minimum,
Then you've reached equilibrium.
okay, so let's unpack the forces that push a system towards that equilibrium. Instability means we have gradients. What are the key intensive variables that are, driving the change?
We really have three main ones. The first is temperature. Temperature is a measure of the intensity of thermal energy.
Right.
So you have a temperature gradient. That difference is the driving force for heat to move from hot to cold until T is uniform. That's thermal equilibrium.
Which, for an isolated system, is just the state of maximum entropy.
Precisely. The second is pressure. P pressure is the potential for large-scale movement, expansion or contraction. A pressure gradient drives mechanical movement until the pressure is the same everywhere. That's mechanical equilibrium.
And the third one, the one that really gets into the nitty-gritty of materials behavior, like something dissolving or solidifying, that's chemical potential, mu.
Mu is absolutely crucial. It's often called a chemical pressure. It's the tendency of a species to want to leave a phase.
Okay.
So if there's a gradient in chemical potential, that's what drives diffusion, the physical movement of atoms, until the chemical potential for that species is identical in all the phases.
So true equilibrium is when T, P, and mu are all uniform. Let's circle back to the main criterion, G, and see how it responds. Starting with temperature.
Yeah.
How does G change if we crank up T but keep pressure constant?
We use that fundamental relationship, dg equals minus sdt at constant P. This immediately tells us a lot about a G versus T plot.
Oh, okay.
The slope of that curve, the partial derivative of G with respect to T, is equal to minus the molar entropy, minus S.
And since entropy, S, has to be positive above absolute zero, that slope must always be negative. G is always dropping as temperature goes up.
Exactly. It's a fundamental downward curve.
Mm-hmm.
But, and this is where it gets interesting, it's not a straight line. The curvature, the second derivative, is equal to minus Cp over T.
Right.
And since heat capacity and temperature are positive, the curvature is always negative. It curves downward, and it gets steeper as T increases because S itself is always increasing.
So let's visualize this. Let's plot two phases, say solid and liquid, on the same graph. How does that picture explain melting?
The phase with the lowest G is always the stable one. So below the melting temperature, Tm, the solid has the lowest G. But the liquid phase is more disordered.
Meaning it has a higher entropy.
A significantly higher entropy, yes. So liquid is greater than solid, and because its entropy is higher, its slope minus liquid is more negative.
Ah, so the liquid's G curve is falling faster than the solid's curve.
Precisely. It's dropping faster, which means the two curves must cross at some point. That intersection is Pm, the melting point, where G solid equals liquid.
And above that temperature?
The liquid curve dips below the solid curve. The liquid becomes the new stable phase.
This whole idea of the entropy difference directly leads to the Van Hoff rule, doesn't it?
It does. Since the curvature is related to minus Cp over T, the phase with the steeper curve, the liquid, is the one with the larger heat capacity. The Van Hoff rule is really just a consequence of this. The phase with the largest heat capacity will be the stable one at higher temperatures.
Let's talk about that exact moment of melting right at Tm. We call this a first-order phase transformation. What does that term really mean physically?
It's defined by which derivative of G is discontinuous. For a first-order transition like melting, it's the first derivatives of G that are discontinuous.
And those are...
Those are molar entropy, S, molar volume, V, and molar enthalpy, H.
So if you were to graph molar entropy against temperature, you'd see a sudden vertical jump right at the melting point.
Correct. The slopes of the G curves are different, so the entropy has to be different. Physically, this is what happens when you melt ice. You're pumping in heat energy, the enthalpy of melting, delta. But the temperature doesn't move.
Not until all the ice is gone.
Right. For that moment, the system is just absorbing energy without its temperature changing, which means it has an effectively infinite heat capacity. That's the signature of a first-order transition.
That really makes it click. Okay, let's pivot. If we hold temperature constant now, how does G respond to pressure?
We use the other relationship, dG equals VdP at constant T. So the slope, the partial of G with respect to P, is just the molar volume, V.
And since volume is always positive, the G versus P curve has to always slope upward. More pressure always means more Gibbs free energy.
Precisely. And just like before, the phase with the larger volume will have the steeper slope. The key physical insight here really comes from the Chatelier's principle,
Which says that if you apply a stress, in this case pressure, the equilibrium will shift to counteract it.
Yes. Increasing the pressure pushes the equilibrium toward the phase that takes up less space, the one with the smaller molar volume.
And this is where the classic water example comes in, showing that these rules have really important exceptions.
Absolutely. For almost every material, the liquid is less dense and has a larger volume than the solid. So for them, applying pressure favors the solid and raises the melting point.
But not water.
But water is the famous anomaly. Ice has a larger volume than liquid water. So if you squeeze ice, the equilibrium shifts to the phase with the smaller volume, the liquid, and the melting temperature actually decreases.
That one exception just perfectly illustrates the power of these relationships. So now we have these two plots, G vs T and G vs P. How do we combine them to predict the equilibrium curve on a PT diagram?
For that, we use the Clapeyron equation. It defines the slope of that coexistence curve, the line where two phases are equally stable.
Okay.
We start by demanding that to stay on that line, any change in G for one phase must equal the change in G for the other. So DGL must equal DGS.
Okay, you set them equal.
You set them equal. You substitute in the full expression for DG with both the S and V terms, and you rearrange. The result is, well, it's a beautiful, elegant equation.
The Clapeyron equation.
The Clapeyron equation. The slope, dP over dt at equilibrium, is equal to delta H divided by T delta V.
That equation is a powerhouse. It gives you the slope of the PT boundary for any first-order transition just based on the latent heat and the volume change.
And it becomes hugely practical when we apply it to vapor equilibrium. This leads us to the Clausius-Clapeyron approximation.
Right, so for liquid vapor or solid vapor equilibrium, we can simplify things.
We can. We make two approximations. First, the volume change, delta V, is just. It's basically the volume of the vapor. The condensed phase volume is tiny in comparison.
You just ignore it.
You basically ignore it. Second, we treat the vapor as an ideal gas. PV equals RT.
And if you plug those in,
You get a much simpler form. D of the natural log of P over dt equals delta H over RT squared.
and that's incredibly useful because if you assume delta H is constant, you can integrate it.
Which shows that saturated vapor pressure increases exponentially with temperature.
And practically, for lab work, you can just plot the natural log of pressure versus 1 over the temperature. It should be a straight line, and the slope immediately tells you the latent heat. That's a huge shortcut.
It is a workhorse equation, absolutely.
Okay, now let's step back and visualize the whole PT diagram. This is really just a 2D projection of a 3D GTP surface. How do the areas, curves, and points on this map relate to stability?
We use the Gibbs Equilibrium Phase Rule for a one-component system. It's F was 3 minus phi. F is degrees of freedom, and phi is the number of phases.
Okay, so the big open areas on the diagram, those are where only a single phase is stable.
Right, one phase means phi is 1, so F is 2. You have 2 degrees of freedom. You can change both P and T independently and stay in that phase.
The curves are the coexistence lines, the ones the Clapeyron equation describes.
On those curves, 2 phases coexist, so phi is 2 and F is 1. You only have 1 degree of freedom. If you pick a pressure on that line, the temperature is automatically fixed.
And the most constrained point of all, where 3 curves meet.
That is the triple point, the invariant point.
Yeah.
Here, 3 phases, solid, liquid, vapor all, coexist. Phi is 3, so F is 0. No degrees of freedom. P and T are completely fixed.
We've covered melting pretty well, but the real complexity in materials science often comes from solid transitions, like allotropy in iron or polymorphism in zirconia. Do the same rules hold?
Absolutely. The G versus T plot still rules everything, and the Clapeyron equation still defines the coexistence curve. But this is where you see some really fascinating behavior, like the famous anomaly of iron.
Right. Iron is BCC, the alpha phase, at low temps, and FCC, the gamma phase, at intermediate temps. But the boundary between them on the PT diagram has a negative slope, just like water. How does it happen?
A negative slope means dpt is less than 0, so delta H over T delta V must be negative.
Okay.
For the alpha to gamma transformation in iron, we know the volume change, delta V is negative. The FTC gamma phase is actually more dense.
So if delta V is negative, for the whole fraction to be negative, the numerator, delta H, or really delta S, must be positive.
Correct. The entropy of the gamma phase has to be larger than the entropy of the alpha phase. And this is totally counterintuitive because the FCC is a more closely packed structure. You'd think it would be more ordered.
That seems to challenge the simple idea that entropy is just about crystal structure, so what's really going on?
It's a beautiful example of non-vibrational entropy. The higher entropy of the gamma phase is because of spin entropy.
Magnetic ordering.
Exactly. The BCC alpha phase is ferromagnetic, so its atomic spins are all ordered. The FCC gamma phase, on the other hand, has a more complex magnetic state that disorders, and that disorder adds a huge contribution, the spin entropy, to its total entropy.
So the gamma phase is stable at high temperatures not just because of lattice vibrations, but because it has a greater magnetic disorder.
That's it. That extra magnetic disorder gives its G curve a steeper negative slope, allowing it to drop below the alpha phase's curve at high temperature. It shows that phase stability is this delicate balance of all forms of disorder, vibrational, configurational, and, in this case, spin.
That puts the whole GVST discussion in a totally new light. So last thing, let's just briefly touch on another external force. A magnetic field, H. What happens then?
When you apply an external field, you actually change the definition of the Gibbs free energy function. And the important part is that the field lowers G more for the phase with the larger magnetic susceptibility G.
So the field stabilizes whichever phase is more magnetic, and it expands that phase's stability region on the diagram.
That's the takeaway. The field shifts the equilibrium curve. And that principle extends to other external fields too, like electric fields.
That was a fantastic deep dive. So to just quickly synthesize this for you listening. First, stability at constant T and P is all about finding the minimum Gibbs free energy, G.
The lowest G always wins.
Second, the slopes of your G versus T and G versus P plots are just minus S and V. This means the highest entropy phase is stable at high temperatures. Third, we classify transitions like melting as first order because properties like S and V jump discontinuously. Fourth, the key equation that defines the slope of all those coexistence curves is the Clapeyron equation. And finally, the number of phases that can coexist is strictly limited by the Gibbs phase rule, F equals 3 minus phi.
The whole field of material stability really just hinges on understanding these relationships. And that discussion on iron and spin entropy, it really highlights that even well-known transitions are often controlled by these subtle, non-vibrational factors. It's a reminder that when you see an unexpected phase stability, you have to look past the crystal lattice and ask yourself, what other kinds of entropy are driving this?
An excellent thought to end on. We really hope this deep dive into phase equilibrium helps you truly understand the forces at play inside materials.